Please answer the question, what do you think? In this situation, we have two balls, number one, number two, separated by a distance, and we know that, like in our experiment on Monday, when only gravity and tension acting on the ball at rest, the string will be vertical. And to deflect the ball, we need to apply certain force. And in this situation, of course, we need to draw a free body diagram. And this part is not new. So let's say we have an object. String. Hold it tightly, and naturally there has to be force of tension. And naturally, because everything is happening here on the surface of the Earth, there is a force of gravity acting on it. And well, to deflect the string from the vertical direction, we should apply the third force, right? So that third force, how does it point? What is the direction? So how do we call that direction? How do we call that direction? Left. So it points to the left. And we have several directions. Yeah, we need to know how to call each important direction: up and down, left, right, into the screen, out of the screen. And here, that third force supposed to be deflecting to the left, which means it has to point to the left. What is it, pushing or pulling? Well, in this situation, nothing is pushing. Nothing else is touching except the string. But clearly, that third force is supposed to be due to the presence of the ball on the left. Now, there is a word which we should describe, which we should use to describe what is happening between these two balls, right? What do we say? Attraction. So the ball on the left attracts the ball on the right. Does it mean the ball on the right repels the ball on the left? What do you think? Say something. I'm not giving up on you. The ball on the left attracts the ball on the right. Does it mean that the ball on the right repels the ball on the left? They attract each other. So, unfortunately, we don't know if the ball on the left is negative or positive. And we don't know if the ball on the right is negative or positive because there is no information about that. So all we can say is they have to be opposite. And of course now we can solve this problem directly because we know how to use a free body diagram. Tension, gravity. And this force has a name, Coulomb's force, electric force. the force of electrostatic, well, attraction in this situation. So let's say electric, not elastic, would have been the same letter. And the ball is in equilibrium, which means the net force acting on it is 0, which means electric force, I said it's not elastic, plus force of tension force due to strain, plus force of gravity is equal to 0. And when people write it like that, they make mistakes. What is wrong with this? Very important. Yes? Right, and how do we indicate the fact that each variable represents a vector? No. So in a textbook, in a modern textbook, to separate a vector from a number, I don't know, it's the author or the editor, they use different font. So if you see this, that normally represents a number. If you see this, that normally represents a vector, and you need to recognize the difference. But for me, every time spending valuable time doesn't make any sense. So I do it once to make a point. But in writing, all variables which represent vector have a little arrow above it. That's how we read it. So here we are adding 3 vectors. Technically, this is what is happening. This arrow plus this arrow plus this arrow together cancel each other out, 0. Now, here we have a fork. We can apply a tail to a head rule we've studied extensively and do it in that way. So tail to a head, then tail to a head, then tail to a head. That will give us a triangle. The fact that the sum is 0 is here in this dot. We begin here and we end back at the same location. So the resultant is 0. That's one way to do it. And there is a second way, is using components. If we want to use components, we need to see the x and y axes. And in this situation, we can write 2 equations. One is relative to x-axis, second is relative to y-axis. And now, relative to x-axis, first arrow has a negative component. Second arrow has one positive component. Gravity doesn't have a component relative to x-axis. So this is basically Newton's second law. For the equilibrium, it has a name, force balance equation. And we can write the same equation relative to y-axis. Relative to y-axis, this arrow has no component. Tension has a positive component, gravity has a negative component, and the resultant is 0. And it doesn't matter how you want to do this problem, using a triangle or using components. The result, of course, will be exactly the same. My triangle should look more similar to the picture, so the angle theta the angle theta should look similar in both pictures. Again, this, now in this triangle, you see, in this triangle, I was adding vectors, so each arrow has an arrowhead. But now, I don't need the directions anymore. Now in this triangle, each side represents the magnitude of that particular force. So this side is equal to the magnitude of electric force. This side is equal to the magnitude of the force of gravity. This side is equal to the magnitude of the force of tension. This is a very well-known triangle. And if you're not sure what to do about it, you should refresh your knowledge, because we've done it in PY 105. For example, I can immediately write this relationship. What function? Tangent. And that will give me what? I know the mass, so I can calculate the electric force. That will give me electric force. 0.1 times 10 times tangent of this. Actually, no. Tangent of this. Okay, that's it. 2 unknowns. Well, that means I gotta do something differently, and I know what to do. If I look at the data, I actually can calculate the electric force directly using Coulomb's law. Coulomb's law tells me that same force should be equal to 3 microcoulombs times 3 microcoulombs divided by distance 0.3 squared. So what does it give me? 9 times 9 divided by 0.09 times 10 to the -12, so -3. Right. Microcoulombs. Okay. So 9 and 9 cancels. 9 times 10 to the 5th, I think. I don't know. Looks huge to me. Well, wherever it is. And now we can calculate the rest. We can calculate the angle. That's always possible to do. So we just have to use the inverse function of that huge number. Maybe I meant millis, not micros. It should work with micros as well, just not very intuitive, but every calculator has different way for calculating inverse functions. So I got 89.99936 degrees, almost 90 degrees. It's supposed to be, so almost horizontal. Well, it's because of maybe it should have been nano, probably. Yeah, not micro. It doesn't matter. Yes? 0.9? Oh, it's -3. It is -3. It's not +3, so I add it. So thank you. That makes much more sense. So it's going to be -1. Yeah, which is 0.9. 0.9, and that changes the angle to more reasonable number. Yeah, thank you. Which is what? 42. Yeah, I remember it was something. And now, of course, we can apply degrees. We can apply, let's say, sine or cosine relationship to calculate the tension in the string, because since we know the angle, tension will be equal to, for example, force of gravity divided by cosine of this angle. That's it. So 0.1 times, so 1 over, bless you, cosine of 42. 45 square root of 2. 1 point something. 1.3. 1.4. 1.35, close enough. So this problem was a review of everything we've learned about forces. That's it, nothing else. We used only one extra equation for calculating electric force, bless you, between two balls. The rest is free body diagram and right triangles. And yeah, okay. Let's move on to the next situation. Here we have three charges, and please draw a free body diagram for the charge on the right, because that's what we need to calculate, the net force acting on that charge. Calculate the net force acting. Yeah, here we have nanocoulombs. Nano means 10 to the negative 9th, so here we assume nothing else is acting except charges. So technically, when it says calculate the net force, it meant calculate the net electric force due to two other charges acting on the third one. And you can see this charge is positive, this charge is also positive, that charge is negative. So this helps us to draw, a free body diagram. Normally, in many textbooks, people use the red color for positive charges and a blue for negative charges. So this is here, this is here. Now we have a triangle. I remember it was a right angle triangle. 30, 60, 90. Okay, so something like this. 30, 60, 90. We have another positive charge here. This angle is given 30 degrees, 60 degrees, and distance between these charges is 3 meters. So is it a 3, 4, 5 triangle? No, of course not. First of all, 30, 60 triangle is not 3, 4, 5 triangle. Plus 3 here is a hypotenuse. So, just make sure 9 nanocoulombs, -4 nanocoulombs, 2 nanocoulombs. Now, for each pair of charges, we have to draw a force acting on the charge on the right. So, red and red repel each other. Force acting, let's column 1, 2, 3. So this is the force acting on the third from the first. But negative and positive attract each other, so that should be force acting on the third from the second. Now, this should be distance between charges 1 and 3. This should be the distance between the charges 2 and 3. Why do we need those? Well, because we need to calculate each individual force first. So the magnitude of this force, 9 nano coulombs, 2 nano coulombs, and well, the distance should come up from the triangle. Bless you. So that should be equal to hypotenuse times cosine of this angle squared. Now, next force should have magnitude equal to Coulomb's constant. Oh, sorry. Today is Wednesday. I have to draw perfect force. So 4 times 10 to the negative 9th, and it has to be positive because we're calculating magnitude, times 2 times 10 to the negative 9th, and distance squared, distance between the charges now, so the side is opposite to hypotenuse, 3 times sine of 30 degrees. Someone can tell me numbers. And now, to get the net force, we gotta add 2 vectors. Again, one vector points like this. Second points like this. And I don't know how long it is because I don't see the numbers. Why? Because no one told me the numbers. So if you tell me the numbers, I will see the numbers. At this point, you want to tell me the numbers? Thank you. Newtons. So this actually should be, this arrow should be longer. Doesn't really matter. Technically, because what matters is this. In this situation, these forces are perpendicular to each other. So they also form a right triangle, which is a good thing. Because when we have a right triangle, we know what to do. This arrow represents the net force now. All we need to do is just calculate the hypotenuse. That will be the magnitude of net force. What do you do if that's not a right angle triangle, if something more complicated? In that case, you will have to use components. You will have to do this. You could have used cosine theorem, if you remember how it works. But in general, you should use components. And here, what we should have is square root of 2.4 squared plus 3.2 squared. It should have the same common factor, -8. Wherever you tell me. So, just newtons, yeah. Again, it's more about triangles than about forces. It's more about geometry than about physics. Question, please. This is a less complicated system. We don't have triangles, we don't have angles. We still have a system when two other charges exert a force on the third one. Of course, they all interact. But the question is, well, what do you think about the polarity? Polarity is the fancy word for sign, plus or minus, positive, negative. The polarity of this charge, if we know that this charge in equilibrium and the only forces acting on the third charge is due to charges on the left. What does equilibrium mean? Net force equals 0. That means force exerted by the first charge should cancel the force exerted by the second charge. And of course, it should be helpful to draw a free body diagram, but something's stopping you from doing that. What? Do you know if the second charge attracts or repels the third one? Can you tell me? What do you think? Charge number 2 acting on charge number 3. How? Why? There is much clearer explanation why we cannot say why. F on 3 from 2. How should I point it? Why, you don't know? What? The sign of what? Of the third charge. So why are you so quiet? If you don't know something and you need it, what do you do? The one nobody is asking. So someone should ask. Please ask. Plus? Question, of course, would it make any difference? That's more important question. Well, first let's keep it a plus and see what's going to happen. And then let's change it to a minus and see what's going to happen. So if it's a plus, it should be repelled by a positive charge. But to cancel this force, to cancel it out, the force acting on the third charge from the first charge must be opposite to this. That's supposed to be the force acting on 3 from 1. In order to have a force like that, what should be the polarity of the first charge? What should be the sign? Negative. All right. Now, let's quickly analyze the situation. What's going to happen if this charge is negative? So now this is supposed to be the force acting on third from second. But now, in order to cancel this force, the force acting on third from first should point to the right, which means this charge now is supposed to be repelled, and to repel a negative charge, we need another negative charge. So it turns out it doesn't matter. Still, the charge number 1 is supposed to be a negative. Now, of course, we can ask a question. Negative. What is the magnitude of that charge? Yeah. To keep the third charge in equilibrium, what should be the magnitude of the first charge if the magnitude of the second charge is given and we see some distances? Well, this is a very simple situation now. Now, let's keep it positive. Yeah. It's more intuitive. So this is a force acting on third from second. This is the force acting on third from first, and these two forces must have exactly same magnitude. That's what this word equilibrium means. Now, how do we calculate the magnitude of a force between two charges? Okay. Charge number 3, charge number 1 over the distance between the charges squared. From 1 to 3, the distance is 3r squared. No one says anything, so I'm just keep going. Third, second, the distance between these two charges is r squared. Yes? Well, you said it. It makes huge difference. People forget parentheses all the time. You forget parentheses, you made a mistake. You don't forget parentheses. You don't make a mistake. You just now keep solving. 3 squared, 9. Well, we can cancel this constant. We actually can cancel r's. R squared, R squared. Sorry. Numbering. Oh, no, that's correct. We can cancel this charge, actually. The value of this charge doesn't matter. So what's left? Hence, magnitude of Q1 over 9 should be equal to the magnitude of Q2. So Q1 actually should be equal to negative 9 times Q2. Q2 is positive. Q1 has to be negative, and that gives us negative 9 times 2 nano coulombs, negative 18 nano coulombs. So, things to remember. First, sometimes we don't really need to know, for example, the distance or discharge. Still, the problem has an exact solution. If we just power through, eventually we get the number. And if you look at the problem and you think, I can't solve it because I don't know r, I don't know the distance, you should treat all unknown variables like you knew and just go through. All right, so 2 small charged spheres are placed. Net electric force on the third charge is supposed to be equal to 0. This problem is the opposite to the problem we just have solved. In this problem, we know the location. In this problem, we are looking for the location. But in both problems, the charge in the equation is in equilibrium. And as we said that's it. Equilibrium means net force equals 0. So whatever force is acting on this charge, they should cancel each other. So let's draw a picture of what's happening. X-axis, we have x equals 0, and we have x equals 0.4 of a meter. And here we have Q1 equals 3 microcoulombs. And here we have Q2, also positive, equals 5 microcoulombs. 5 microcoulombs. Now, technically, the third charge can be placed anywhere, but there's only one specific location where it will remain in equilibrium. Where can I place it? Here, 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 somewhere here, somewhere here, somewhere here, somewhere here, somewhere here, somewhere here. These are 9 locations which exhaust all possible situations. Now we need to analyze each location one by one and eliminate all of those which don't give net force equals 0, never ever. For example, if I place my third charge here, and I remember we are told it was positive, what should be happening? Oops. Well, the charge number 2 is supposed to repel it, and the charge number 1 would be nice having a ruler. Yeah. But technically, this is the direction of a force acting between those charges. So this would be force, let's call just 1, 2, and if we add them up, they will never, ever give us 0. So same elimination method would give us etc., 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 etc. That's a good exercise to do at home. Here, the third charge, in that case, the force from a charge on the left points to the right, and the force from a charge on the right points to the left, and these two forces at a certain location will have exactly the same magnitude. And that's what we're looking for, this location, basically. And all we need to do again set up the magnitudes equal to each other. That's what the word equilibrium tells us. Now, K, Q1 times Q over distance between the charges squared. And that's what we're looking for. Should be equal to K, Q2 times Q over. Now, if you've done this problem, similar problem with a moon and Earth and a satellite, you know what distance should we write? What should we write for the distance squared? A distance between the charge number 2 and the charge Q. Yes? Exactly. That is the distance between these two charges. And now again you know what to do, because we have solved this problem. Mathematically, this problem is absolutely identical to what we have solved before. So first, let's see what we can cancel. K and K, Q and Q. Now what we can do, we can flip the whole expression to bring the unknown into the numerator, and we can take a square root of both sides to get rid of a square. So what's left is x over square root of the first charge should be equal to 0.4 minus x over square root of the second charge. Do I have the answer? No, I don't. So x times the square root of the second charge should be equal to square root of the first charge times 0.4 minus 6, or square root of this times 0.4 minus square root of this times x. So x will be equal to square root of this times 0.4 over square root of this plus square root of this, wherever it is, I have no idea. What charges do we have? 3. So again, 3 and I think 5. Yeah, 5. That's the answer. At this time, just have to take a calculator and calculate it. Yes? Why what?
Why the Q can be.
For example, this one.
Yeah.
Well, because in this situation, it would have been repelled by both charges. They're all positive here in this problem. So net force actually would have been stronger than any individual force because we have to add them up in the same direction.
So how can it be repelled by both?
Which is negative.
Q1
No, they're both positive. 0.3 and well, just yeah. So you're getting ahead because the question, what I want to ask now, is about the location when one charge is negative. Again, all we change is a sign of a second charge. First charge is still positive, still located at x equals 0. Second charge is located at x equals 0.4, but now it is negative. And technically, again, you need to try out all possible locations. U1, 3 microcoulombs. Q2, 5 microcoulombs. I read exactly the same slide you read.
How did you know that charge?
Because I read exactly what you read. First time, it was a different question than we have now. So you always have the answer number 4. Impossible to tell. And again, theoretically, we should check 9 locations. And theoretically, we should check it twice. First time, assuming the third charge is positive. Second time, assuming the third charge is negative. So 9 times 2, 18. So you gotta walk through 18 reasonings. And eventually you should make a conclusion. Where should we place it? To the left of the first, between the charges, to the right? Or it's impossible to tell. Of course, locations above or below can't be chosen. forces must be horizontal in order to be able to cancel each other. So technically, all you have to choose is here, here, or here. Now, can you choose it here? Between? No. Let's say it's positive again. In that case, a positive charge will repel it, and a negative charge will attract it. So in that situation, forces acting on the charge will point in the same direction. They just can't cancel each other. Now, here, you should have a force, again, let's say it's positive. You should have a force acting to the left and a force acting to the right. Here, you should have a force acting, attraction to the left and repulsion to the right. How can we make a choice between the point on the left and the point on the right? Well, we have two options. We can just guess and solve it, literally, mathematically, and see what we get in the end. Or we can try to analyze what is happening to the magnitudes of those forces, right? Magnitudes should be equal to each other. So force number 1, that's the force due to the first charge. Force number 2, that's the force due to the second charge. So here, that should be F2, that should be F1. Each force is proportional to, well, 1 or 2. 1 or 2 is proportional to the charge and inversely proportional to the distance squared. So, what do you think? Can we balance the forces on the left, or can we balance the forces on the right? This is 3. This charge has magnitude of 5. 5 is greater than 3, right? So here, if I place the third charge here, this force should be, how do we finish it? Stronger, equal, weaker, greater, equal, less. Here, this force will be stronger. You have shorter distance. You have shorter distance and you have stronger charge. So theoretically, only one place. So this arrow always should be longer. So what's left here? And now we just have to solve it. All right, so again, let's make this x. That's what we're gonna find. We use a variable x to read an x coordinate of a point or of an object. So technically, if I set this to 0, this number should be negative, and I like negatives. So I want to introduce a variable which will be positive, d, which is just magnitude of x. If I find d, my x will be just negative d, but d is positive. And well, now again, k q1 q over q1 q over d squared should be equal to k q2 q over, what is the distance from the second charge to the location of the third charge? It should be now 0.4 plus d squared. That's it. And starting from this, you just have to do the same mathematics and solve it for D. Nothing new. What would happen if I guessed wrongly? Nothing serious. Eventually, I would just get a negative number for the distance, but distance can't be negative. So that would tell me I guessed wrong. That's it. Now we're going to talk about a very important in physics field, this word, very important term, category. Field is something which is presented in a region of space. Basically, that's what a field is. Yeah. And sometimes we really don't care what is the source of electric force acting on our charge or our charges. We just need to make a statement about the presence or the absence of that thing we call electric field in this particular region of space. How do we do that? Well, we know that if we take a ball attached to a string, charge the ball, if the string deflects, there's supposed to be a force acting on it. We have solved a problem about it. So what we can do, we can have a ball attached to a string, have it charged, and just walk around. If the string is vertical, means electric force is not acting here on this ball. And we say there is no electric field here at the location of this ball. But if we observe some deflection, that means somewhere other charges create a force acting on this charge. But we say simply there is electric field at the location of this charge, which is responsible for the existence of this force. That's it. Now, of course, we need an official definition. And again, we have to imagine, for example, a charge on a string, which means we can calculate the force. We did it just, I don't know, 50 minutes ago, right? And we created that charge, so we know the value of this charge. Now, if we calculate this ratio, the result has a name, electric field strength. It demonstrates how strong electric field is here. That's it. Now, a force is a vector, a charge is a number. So a vector divided by a number, or a vector multiplied by a number, is still a vector. So this variable, E, which represents electric field strength, but no one calls it electric field strength. It's too long. Everybody calls it electric field. That's it. So there's electric field of electric field, which means electric field strength of electric field at the location of this charge. This charge has a name, a test charge or a probe charge, because we use it to test the presence of electric field. And of course, the easiest test charge would have been 1 coulomb. Because if we multiply by 1, or if we divide by 1, we get the same thing. So electric field basically is just a force acting on a positive 1 coulomb charge. That's it. What do we know about electric force? By now we know everything. Which by transition property, by now we know everything about electric field. Because if you read something like this, you can just imagine that a positive 1 coulomb charge is placed at certain location and just do forces. There are other approaches, of course, but this will always do. Any questions? This is just a definition so far. Question? This is a definition of electric field that new physical quantity we use to describe the presence of something in a special region. Basically, electric field makes this region be different from this where there is no electric field. It's more tense. And this arrow represents a force acting on a negative charge. Some other charges, of course, are responsible for the existence of electric field at the location of this negative charge. And it's time to take a look at how Webassign is doing. 1, 2, 3, 4, 5. So far only 10 students, so I want more. Represents a force. First of all, we don't like fractions. Normal people don't like fractions. So that equation usually people write differently, like this. Or even like this, because we don't really have to show every time that we use a test charge or what kind of a charge, so we don't really have to use that subscript. A force acting on a charge from electric field is equal to the product of the charge and electric field strength at the location of the charge. That's how we read it. And if I take a vector, which is an arrow, and multiply by a positive number, the result is an arrow, which points in the same direction. How do I know? I learned it in school some time ago. Now, if we take an arrow and multiply by a negative number, the new arrow will point in opposite direction. That's it. So the answer here is, if my force points to the right, but the charge is negative, that means the electric field should point to the left. So a rule is simple. If electric field is acting on a positive charge, electric field and force point in the same direction. If electric field is acting on a negative charge, electric field and force are opposite. That's it. That's pure mathematics. Technically, what we're doing here is this is equal to some negative number times a question mark. Technically, that's what we're doing. We're solving an equation. So the question mark should be equal to, well, this arrow divided by some negative number, which means it should be some opposite arrow. Maybe longer, maybe shorter. We don't know that without numbers, but we definitely know the direction because of this information. Any questions? That's not a question for the Webassign. Let's just think about it. Now we know how to approach the relationship between electric field and the charge. Here, if we draw a free body diagram, this arrow should represent the force of tension. This arrow should represent the force of gravity. In order to be deflected to the right, we should have electric force pointing to the right. But electric field shown to us points to the left. This arrow represents electric field at the location of the charge. And these variables, electric force, charge, and electric field, are related by this equation. And we know for the positive charge, these arrows always parallel. For the negative charge, opposite. Since they are opposite, this should be a negative charge. And, well, what can we do now? Now we can do some algebra again. Tension, gravity, and electric force. Tension plus, let's say, gravity plus electric force should be equal to 0, equilibrium. So again, we have a triangle. And in this triangle now, if I use only magnitudes, this should, the hypotenuse should represent the magnitude of the tension. This vertical side should represent the magnitude of gravity, and this should represent the magnitude of electric force. Nothing new. The only new equation now is this. If we want to, we can relate the magnitude of this electric force with the magnitude of electric field. And of course, there might be an angle involved. So we immediately can write the same expression or how do we solve it depends on what we know and what we are looking for. Okay, we have numbers, so I'm going to do it with numbers. This is a very important note. See, we have two types of equations. This equation and this equation. And the first equation relates vectors. Second relates magnitudes. People very often use exactly the same letter, Q. But in different equations, the meaning of that letter is different. In this equation, this is actual value, actual charge. If it's a positive charge, this is a positive number. If it is a negative charge, that's a negative number. But in this equation, that Q represents magnitude. So I always like to show it explicitly, but you don't have to, you just need to remember. So in this equation, this Q represents the actual value of a charge. And if we want to solve this, what do we know? We know E, strength. I didn't mention actually the unit, force over charge, Newton over Coulomb, the unit. And we know the angle. I think I have it solved. So yeah, in this equation, Q represents the magnitude. All right, so quickly, very, very quickly. First of all, if the angle is 45 degrees, that's 45. This is 45. This is 90. That automatically means that mg and QE are equal to each other, same sides. And if we need to calculate the magnitude of the charge, mg over E, 0.1 times 10 over 100, 0.01 over coulomb. Wherever it is, it's still too large value. Usually, charge we can achieve by just rubbing, for example, is much, much less. Any questions? So, calculate the magnitude of the electric field generated by a positive 10 nanocoulomb source charge at the location of a test charge located 30 centimeters away from the source charge. All right. Please calculate the magnitude of the electric field. So a source charge generates electric field. A test charge is feeling electric field, but it all in our mind. We could call them differently, yeah, opposite. It all depends on the specific situation. I think yeah. So a positive source charge, let's call it Q, 10 nanocoulombs. And somewhere in space, we don't know where exactly, maybe to the right, maybe to the left, maybe even like in the picture, somewhere here, we place a test charge at 30 centimeters or 0.3 kilometer away from the source charge. Here, we are calculating or maybe even measuring electric field strength. The source charge generates electric field everywhere, so we can walk and measure the strength, but particularly here. Now, what would be the easiest, the most convenient test charge? We can choose it because there is no information. So what is the easiest, the most convenient value for a test charge? What do you think? Yes? 1 coulomb. According to a definition, electric field strength is equal to the magnitude of a force acting on a 1 coulomb test charge. So how do we calculate it? We're just applying the Coulomb's law directly, straightforwardly. 9 times 10 to the 9th, 10 times 10 to the negative 9, 1 over 0.3 squared. So that's 9 times 10 over 0.09. 1,000, right? And Newton over a coulomb. Would it change the strength of the field if we used a different test charge? No, it wouldn't. Because first we could calculate force acting on a new charge and then divide it by that charge. So it gives us a way of calculating, I'm going to add it here. it gives a way of calculating electric field strength of a single charge. Let's say we have a positive charge, Q, and let's say we are here, R meters away. So electric field strength here should point away from a positive charge. Why? Because if we would have placed 1 Coulomb test charge at this location, it would have been repelled away. So that's electric field strength. And the magnitude of that electric field strength due to a single charge should be equal to this, this, times what? Well, technically times 1. Yeah, there's always that invisible 1 Coulomb, but why would we write it? It doesn't change anything. So this is how we always can calculate electric field strength generated by single charge. What if we have 2 charges? Don't answer this question. So let's just do it. Now, each charge generates electric field. The charge on the left, positive one, generates electric field at the point P. And the charge, well, in the middle, also generates electric field at the point P. Well, we can always imagine that right here we have a positive 1 Coulomb charge and just calculate the net force acting on it. So how would it look like? Well, let's call it number 1, number 2. As we just said, electric field of a positive charge points away from that charge. So right here I should draw an arrow. I should call it E1. And this arrow represents electric field of the first charge at point P. And it's very important to be able to say the whole thing. Electric field generated by this charge at this point. Because if you draw electric field vector, this arrow, it should begin at the point where you're measuring or calculating that arrow. And it should point away from a positive charge. But a negative charge generates its own electric field. So what do you think is the direction of the electric field generated by a negative charge? What do you think? Exactly. It should be opposite to the positive one. So this arrow represents electric field due to the negative charge. Well, first we should calculate each strength individually. E1 equals K Q1 over R1 squared. It's supposed to be 9 times 10 to the 9th. First charge, 3 nano coulombs divided by, well, the distance has to be measured from the source to the point. 3 and 4, 7 meters. Supposed to be squared. That's got to be newtons. Now the magnitude of electric field at the same location from a second charge, what should we write? K, magnitude of the second charge, distance number 2 squared. We are calculating magnitudes, it's very important. 9 times 10 to the 9th. A perfect 4 times 10 to the negative 9th. Distance from a source to the point, 4 meters squared. Well, now we need to do vectors. One arrow points to the right, second arrow points to the left. So net arrow relative to the positive x direction should be equal to the x component of the first arrow plus the x component of the second arrow. The first component is positive, second actually is negative. That's what we need to calculate. So now, someone should tell me the answer. Technically, that could have been this. 9 times 3 over 49 minus... Which one? Well, it's given 3. Oh, it's 9. Someone really hates me. Thank you. Nine, 49, and minus 9, 10 to the 9th, 10 to the negative 9 getting cancelled, over 4, because 4 and 4 squared. $81 over 49, whatever it was, please tell me. Negative 0.59. Could it? Okay. What does it mean? It means that the actual total electric field points to the left. That's what it means. It means actually my red arrow should be shorter than my blue arrow. That's it. A Newton over a Coulomb. Any questions? So technically, a problem related to calculating net electric field is no different from a problem for calculating net electric force. Okay, again, not a question, but we know what to do. Technically, all we have to do is to analyze 9 different regions. And we didn't say it last time, but we could have used a negative charge. It wouldn't matter, because if the net field is 0, you're multiplying positive charge or negative charge times 0, still going to be force equal to 0. So you can use positive test charge 9 times. And we know from the past that in order to cancel forces, the test charge should be closer to the weaker and farther away from the stronger charge. Otherwise, the stronger charge generates the forces too strong. So in this situation, what's left is here. Well, this is our assumption. A positive charge should be repelled by a strong positive charge and should be attracted by a weaker negative charge. So these forces should be able to cancel each other. It is handy to actually draw electric field generated by each charge, like in this picture. What you see here is this arrow, well, technically it should be here, represents electric field of this charge close to it. But if we move away, distance squared. So we don't change the direction of the arrow, but we change its strength, its magnitude. So it's getting shorter and shorter and shorter. Same is happening here. Electric field points away from a positive charge. Away means away in all directions. So on the left to the charge, electric field points to the left. But if we move away from a charge, the strength becomes smaller and smaller. Same here. This is a negative charge. Electric field should point at it from all possible directions. So this is an arrow relatively close to the charge, but if we move away, it's getting weaker and weaker. And here, technically, this arrow could have canceled, but in reality, it's not going to happen because this will be much stronger than this one. And now, of course, we just have to solve this problem. So if we know the direction, if we know the location, if we know the direction of each electric field, we know the location, all we need to do is, well, call it Q1, call it Q2. Q1 is positive, Q2 is negative. And now we have to say that electric field strength due to first charge should have the same magnitude as electric field strength due to the second charge. That's it. You could have said that electric force acting on a test charge placed at this location should be equal to 0 net electric force. But force divided by 1 coulomb gives you field. Same thing, nothing different. What equation should we write? K Q1 over, well, Q1 is positive, so distance x squared. How do I know? Well, it's given to me. This is what I'm looking for, x. Should be equal to the constant magnitude of a second charge. And now I need to do this distance. Well, now the geometry tells me this distance should be equal to x minus 4 centimeters. Let's convert into meters squared. We have solved this type of equations probably 4 times already. We know what to do. Cancel things we can and do the math. And if you do the math, you get the result. At this point, nothing new at all. Nothing new at all. That's why instead of doing it, I'm just pointing at it. We've done it before. This will be question number 7. I want to ask you this question. What do you think? Some charges somewhere in space far away from where we are here, measuring electric field. Those charges generate electric field. I can measure the net electric field. This is what I really measure. But since we know how to use vectors, I can resolve a vector into the components. This will represent electric field from those charges. This will represent electric field from those charges. The question is, what do you think about those charges? Negative, positive? And the answer is, what do you say? What do you say? Both sets are positive. What do you say? You just, I saw your eyes. You just finished reading it, so. Not sure? Well, we need to apply the rule we know already. We know that for a, for a positive charge, everywhere around it, close or far away, electric field points away. Away means you draw a line, maybe imaginary line in your mind, and that arrow should represent electric field vector at this location or at that location. Away. For a negative charge, electric field vectors should point to it, toward it. So toward means this way, or this way, or this way, or this way. And if we look at the picture, this points away from B, this points away from A. Away means positive, so of course in this situation they should be positive. That's it for today. I'm going to start from this problem tomorrow. And someone left a calculator. Really, please don't forget to pick it up. Now, if you didn't do it, if today is your first day, I need your honor code signed. And please, before you leave, stop by and leave your signature.
I came yesterday, but I couldn't sign into Webassign, but I did sign over here.
You mean Monday?
Yeah, Monday, I'm sorry.
What about now? Do you still have problems with them?
No, I signed in and everything.
Okay.
Also, I sent you an email.
You should send me an email
Okay.
just saying what you just said.
Okay, awesome. Also, I emailed you for your lab question.
I think I did I answer?
You did, but so you said lab 5 would be ideal, but I can only attend the one that are 11 in the morning. Is there any chance I can be part of one of them? It doesn't matter which one. It's just only if it's in the morning.
In that case, probably better if you go in a Tuesday, Thursday.
Okay, yeah, absolutely.
All right. In that case, I forgot. You want to permanently switch or just one time? In that case, please bring the form.
Okay. I'm sorry, I'm not a student here. What form is that?
Add/drop
Okay.
form. You can find it upstairs in the office. Just ask whoever, you know,
Okay, okay.
on the
Awesome.
reception desk.
Okay.
They have, and you can fill it up. It says drop this section, add this section. I will sign it. You can bring it back, and they will switch it permanently on the student link.
Awesome. Thank you so much.
No. Keep it there. Thanks. No, I mean that thing. The projector. Keep it there. Yeah. Yes.
Kind of an unusual question.
Yep.
I'm dog sitting for my parents
Yes.
Sunday this weekend. Can I bring my dog to class on Friday? She doesn't bark or anything. If she's like disruptive, I can always leave. But if I just sit in the back, is that okay?
Well, we can try and see how it goes. Okay.
Okay, yeah. If she's like annoying at all, I'll just leave. But thank you.
Hi.
Hello.
Tomorrow I have a doctor's appointment at 8:30, so I don't know if I'll be able to make it back on time for the lecture. As for like the Webassign,
Well, if you have a doctor appointment,
I have like I can.
you can go to a doctor and send me an email about that. And
I have like the mail confirming the appointment, so I can forward that to you.
well, you can forward it to me. You allowed to miss 5 lectures, I think, or 4. Well, on the syllabus it says the number of lectures. You can just, if you have
An excuse.
an excuse, yeah, you can, but you just need to send me an email about